Yes, it's now started recording. Okay, sorry. So, uh, here in this question we have a velocity field v bar equals to 3x square y I cap plus 2xy square j cap plus 2zy plus 4t k cap. This is the velocity field we have. And now the question is about find out the vorticity at the point 1, 2, 3 and time t equals to 3 seconds for the velocity field. This velocity field. So how do we find the velocity field? What is the equation behind that from our understanding? Velocity field. First of all, we need to understand where is the vorticity is we are seeing. We can say vorticity omega. We know that is equals to 2 angular velocity. It is the angular velocity, where angular velocity is can be written as in 3 directions: y j cap plus omega z k cap. So we have, this is our vorticity. Vorticity equals to 2 times of omega bar, and that omega bar, omega x I cap omega y j cap plus omega z k cap. So we have an equation for this omega, that is del cross of velocity bar. How to find out this omega bar, and we need to substitute this in vorticity function, then we can find the vorticity of this velocity. So how to find out this omega bar? Omega bar equals to uh, one more thing, we can write it like as is a del cross v. Del cross v bar, half del cross v bar. How do you find out the del cross v bar? Del cross v bar equals to modulus of, or the determinant, I cap j cap k cap dou by dou x dou by dou y dou by dou z. This is the, and u v w. Determinant of this matrix will give us the del cross v bar, the cross product. So once we do the cross product, we will get omega bar equals to half, let me write, dou w by dou y minus dou v by dou z, and then this is I cap minus dou w by dou x minus dou u by dou z, and this is j cap plus dou v by dou x minus dou u by dou y, and it is k cap. If we do this determination, then we can obtain this omega bar. So now our task is to identify what is w, v and u v and w. From our velocity vector, v bar equals to 3x square y I cap plus 2x square y, sorry, 2y square. Two xy square j cap plus 2zy plus 4t k cap. This is our velocity field. In this velocity field, we need to separate that u equals to 3x square y, v equals to 2xy square, and w equals to 2zy plus 4t. Now we need to just substitute this into the omega bar equation. Omega bar equals to half of dou by dou y of w is 2zy plus 4t minus dou by dou z of v is 2xy square Now let's simplify in the step by step. If we differentiate this, you will get 2z plus 0 minus dou by dou z of 2xy square is 0, and then the second part again we will say this is multiplied by I cap. Again let's so the second part we have dou by dou x of w is 2zy plus 4t, okay, minus dou by dou z of u is 3x square y. This will give you, we have one more half here, yeah, okay. So this will give you half dou by dou x of 2zy, this will goes to 0, and 4t, this will also goes to 0, then 0 minus, and here also we have minus, so this comes to minus, and dou by dou z of 3x square y, there is nothing variable here, z variable, so it will also goes to 0, and then our last one, third part, dou by dou x of v is 2xy square minus dou by dou y of u is 3x square y is equals to half, this is minus, yes, is equals to half of dou by dou x of 2xy square is 2y square minus dou by dou y of 3x square y is 3x square. So these are our vorticity parameters. Let's substitute these things in omega. So omega bar equals to, if we take out half as a common, 22 I cap minus 0 j cap plus 2 y square minus 3x square k cap. I hope you can see the window. So omega bar equals to, this is our equation. Now the question is to find out the vorticity. Vorticity is equals to 2 times of angular velocity. So this half will go away, then omega is equals to just this value plus 2y square minus 3x square k cap. Still the question is not complete. The question is like substitute the values of 1, 2, 3 in x, y and z components at time 3 equals to 3 seconds. So there is no time parameter obtained in our omega equation. So it is like a steady vorticity. Vorticity is not it's not depending on the time, and so if we substitute our spatial coordinates, we will get 22 I cap minus 0 j cap plus 2 y square. This is a 22. I think this is sorry. Here it is 2z. This is 2z. Okay. Yes, it is 2z, not 22. This is 2z and 0 j cap, and 2 into y square means y value we have 2 square minus 3 into x value we have 1 square k cap. Then you substitute z equals to 3 here, then omega equals to 6 I cap minus 0 j cap plus 4 to 8, 8 minus 3, you will get 5 k cap. This is your omega or the vorticity equation. So this is how we need to find out the solution for this vorticity function from our vorticity vector from the given velocity field. Any questions?
Sir, Hello,
Yes,
sir.
Arya.
Can you just repeat the last step?
Which one? Omega equals to
Last
2.
last two steps, yes, sir.
It's not
From
22,
that,
it's 2z. Is this your confusion?
yes, sir. Actually, I was unable to follow you that time.
Yeah, you like where did you miss? Like, did you understand up to
Yes, sir.
uh,
I understand the whole sum, but last two lines means from that how you implemented that points that 1, 2, and 3. Can you
1,
just
2, and 3? They give the values like x value,
oh
y
you
value,
are
and
just putting it in x, y, and z.
yes, yes.
Okay, sir.
It,
Okay.
this is the values that are given for you x, y, and z. This is the z value. I by mistake wrote this a 22, so it's a z. So you just substitute your 2z and y and x values, then you will get it. Okay, let's go to our next question. Yeah, it's recording. So in this question, we have, let me take a pointer. Okay, state true or false for a flow field given by u equals to xy, v equals to half x square minus y square, w equals to 0. They gave a components of the velocity vector instead of as a vector form. The flow is rotational. We need to identify whether the flow is rotational or irrotational. Then only we can state whether it is a rotational flow or whether it is a statement is true or false. To identify whether a flow is rotational or irrotational, we need to understand the condition mathematically how to state a rotational flow and irrotational flow. Suppose for to find a rotational flow, as they given, rotational flow equation is del cross V bar should not be equals to 0. Then only we say it as rotational flow. If del cross V bar is equals to 0, then it is a rotational flow. For your understanding, I am just writing the del cross V bar equals to I cap, J cap, K cap, dou by dou x, dou by dou y, dou by dou z, and then u, v, w. This is the del cross V bar, a matrix that we need to find out its determinant to understand whether it is a rotational flow or irrotational flow. Just substitute the, if we find out the determinant, if we get the determinant, this will be like, let's solve for the determinant. Like I just want to multiply for you again, that is dou w by dou y minus dou v by dou z I cap minus this is dou u by dou z minus dou w by dou x j cap plus dou u by dou y minus dou v by dou x, and this is k cap. So this is what we need to find out, and we need to substitute our u x given u value, v value, and w value. We just need to substitute this, and since our w equals to 0, we can simplify directly some part. So this will go away, this will go away. So these two things will go away, and then we need to find out for the remaining things. And you also see there is no z component in u and v, so this also will go away, this also will go away. So you will left with del cross v bar equals to dou u by dou y dou v by dou z, that is k cap. See, our equation itself has only x and y variables. There is no z parameter both in u velocity and v velocity. Since there is no z parameter and there is no w velocity, and z velocity is also not function of any variables, it's also 0. We ended up with the two-dimensional form of rotational flow, like whether it to judge two-dimensional flow like x and y variables, whether to judge its flow is rotational or irrotational, this simple format is sufficient for our understanding or for our determination of rotational irrotational flow. So let's substitute this. Dou by dou y of u equals to xy minus dou by dou x of v equals to half x square minus y square. And then now see, dou by dou y, this will give it to x, and then half, you can take it out, you will get here 2x. If you simplify, this will give you 0. So since del cross v bar equals to 0, the solution is, or the flow field is, irrotational flow. So the statement is false because they gave it a rotational flow. Okay. Any doubts? Okay. Let's go to the next question.
No, sir.
Thank you. Thank you. Okay. Now, in the next question, we have some interesting problem. Like this is based upon your understanding on the flow physics with respect to pressure and velocity points. How you can determine, and based if you see any flow field, like which option. Let me read the question. Which option is correct for the following statements? The statements are like this. A gradient line is a line drawn in coordinate space along which del P is tangent at every point. Statement 2. The gradient line and iso line through any point in the coordinate space never intersect. And we have true or false only, like asking whether how many statements are true or how many are false. So they're basically asking about a gradient line is a line drawn in the coordinate space along which del P is a tangent at every point. To understand, I will just draw the flow field for your better understanding. So let's consider x and y flow field, and you have iso lines of a pressure. Iso lines of pressure means along this line in your flow field the pressure is constant, say it is P1, and consider another line P2 and one more line P3. So this is your flow field, and we have P1, P2, P3, these are all iso lines. Along this line your pressure is constant. Now consider a vector. It's a scalar field. If you want to understand any scalar field in which direction it is increasing more rapidly, you need to find out its a gradient. That's what the gradient means. Del P, del of P. This will give you the maximum rate of change of this scalar field. Suppose if this is your scalar field and this is the maximum rate, and if you try to find out these lines, these gradient lines, and suppose P3, these lines will pass like this. These are all the gradient lines. That means you can say it's a differentiation of, or I will write your gradient for you. Dou by dou x plus, this is I cap, j cap plus k cap. This is your gradient. This will give you the vector. So these are all the gradient lines, these dotted lines, and say P3 is greater than P2 is greater than P1. Now if you see, according to the statement they given, a gradient line is a line drawn in the coordinate space. Yes, we drawn a line in the coordinate space of xy, and along which del P is tangent at every point. Yes, how we drawn this gradient line means the definition itself is along these lines, these gradients are, the pressure gradients are tangent. The pressure gradient gives the direction of how at maximum change in that scalar field, like pressure field, the rate of change, which direction the pressure field is changing at maximum rate. So those are your gradient lines. So you must remember that P3 is greater than P2 greater than P1, then only this gradient lines will pointed out in this topward direction. And next question, next statement they gave is, the gradient line, that is the pressure gradient line, and the iso lines through at any point in the coordinate space never intersect. If you see, try to analyze this flow field in the xy spatial coordinates, everywhere the iso lines and the gradient lines are intersecting. These are all the intersection points. So the statement saying that these lines won't intersect, but these lines always intersect in a flow field. So the second statement is false. So first statement is true and the second statement is false. This is your solution. Okay.
Sir. Hello?
Yes. Yes, sir.
Sir, can you just define these isolines, means the gradient line and isoline?
Isoline, suppose, let me draw a pressure field with values. This is my xy coordinate space, and I am just identifying pressure and velocity fields at these grid points. Okay, and now suppose my pressure is like this. Here it is 30 pascals, 30 pascals, 30 pascals, 30 pascals. If I join all these points, this is the iso line of pressure, because along this line the pressure is constant, that is 30 pascals. So we call as the P1, that is iso line of P1. P1 indicates 30, where it is 30 pascals is constant. If anywhere in the point, anywhere on this line, the pressure is 30 pascals. So that's why we're calling it as the iso line. Now, if you find out another isoline, suppose another isoline is passing like this, and one more isoline is passing like this, and this isoline is having 27 pascals, and this isoline is having 35 pascals. Can you tell me which direction the gradient will be? Okay.
30, sir, from higher pressure to lower pressure, it will be.
No, from gradient will be in the lower pressure to higher pressure. The gradient definition is, it will give you the direction of maximum rate of change. The rate of changing is in this direction. Okay.
Okay, sir.
So this is your, if you find out a gradient at every point, gradient at every point means if you have a p as a function of x comma y, you just substitute this function p of x comma y in this equation, you will get some kind of vector, like in this form, vector x I cap plus y j cap. This kind of vector you will get, and if you substitute every values of x and y at every point, you can see the direction of it, like 3x cap or 5. This will give you the direction of that vector in the pressure gradient field, and its magnitude also you will get from that. So if you join these lines as a tangent, making these lines as tangent, this will give you the gradient lines. Okay.
Okay, sir.
Yeah, so intersecting of these points always happens in the flow field. So that's why the statement 2 is false and the statement 1 is true. Fine. Let's go to the next question. This is, I think, one more question we have. Let's see. Here we have that infinitesimal fluid element. Pointer options. An infinitesimal fluid element with A, B, and C. I will tell you the directions of this. These directions are very important now to understand. And fluid element moving in a two-dimensional flow field in the xy plane. It is moving in the xy plane two-dimensional. Assume that at t equals to 2 seconds, the shape of this fluid element is rectangular. So the initial time at t equals to 2 seconds, you have the fluid element with a rectangular kind of shape, and due to the translation and rotation of the fluid element in the flow, this fluid element is translating and rotating in the flow. Its shape becomes distorted as shown in the figure below. So like this, its shape becomes distorted after translation and rotation. Initially it is rectangle, but later on it becomes a kind of rhombus, a rotated kind of rhombus. and then figure below at t equals to 5 seconds. It happened after t equals to 5 seconds. Determine the angular velocity omega z in radians per second of the fluid element. We need to find out its angular velocity. We have been doing that with the velocity field in past 2 to 3 questions. Now we need to identify from the shape of it. And the notations, counterclockwise rotations by convection are assumed as a positive in sign convention. The sign convention is counterclockwise is positive and clockwise is negative. So the solution is like this. Suppose if you have v bar equals to u I cap plus v j cap plus w k cap, you can find out the omega z, or if you have only u and v velocity components x and y directions only, you can find out by using the del cross v bar, or the already thing we already seen, that dou v by dou x minus dou u by dou y. This is k cap. This is how you can find out the omega z. But now we don't have any information of the velocity field. We have only the information of del theta 2 del minus del theta 1. But the angular velocity, if we see the basic definition of the angular velocity is, the basic definition angular velocity starts with the amount of angle, rate of angle deflection, this deflection, if you can see or not. Yeah, I think you can see. These angle are the key parameter. This rate of change of this angle is the key parameter to understand the change in angular velocity, or the angular velocity at that point. So how we can write from that angular velocity? Sorry, let me take pen. Yeah. So omega z, this is in our z direction, that is plane normal perpendicular to the plane, is equals to half of, we need to take the average of these two rate of change of angular deformation. This is the basic definition. Upon simplifying, let me write it completely. Okay, omega z equals to half of d theta 1 by dt plus d theta 2 by dt. This is the basic definition of the angular velocity. We need to do the average, because here also you have one angular velocity at this place, and here also you need to have one angular velocity. To understand the net angular velocity, you need to take, you are taking the average of it. So upon simplifying by assumption of that relating that d theta by dtt, which is proportional to dou u by dou x, or velocity with u proportional to dou u by dou x, we found out this kind of relation. But this is a basic idea of finding the angular velocity. So now we need to just substitute this theta 1 and theta 2. We have dtt, the change in time, as 5 to 2 seconds. The time changes you can see. After 5 seconds, this is the shape, the angular deformation is like this, and initial time it is 2 seconds. This is the dt, and this is your del theta or d theta. Let me write in much simpler format. As we have incremented values but not a continuous one, I can write it as del theta by del t, so 1, plus del theta 2 by del t. Okay, now del theta 1, if you see, it is in the clockwise direction, that's why they mentioned it as negative. Clockwise direction 10 degrees, and this is del theta 2 is in anti-clockwise direction, that is 15 degrees. We have to use the same sign convention to get the exact correct result. So this is half. They asked us the result to find out in radians per second, but they gave the values in degrees, so you need to convert that angles also in degrees, that is minus 10 into pi by 180. This is how you can convert from degrees to radians, plus 15 times pi by 180. This is your del theta 1 converted into radians, and the del theta is change in time 5 to 2, sorry, 5 minus 2 by 3. If you simplify this, you will get pi by 6 times minus 1 by 18 plus 1 by 12 is equals to pi by 6 times minus 2 plus 3 by 36. is equals to pi by 216 radians per second. So this is your solution, and this is the angular velocity of this fluid element. Okay, now let's go to the last question. Last two more questions we have in this session, not in this chapter. We have one more chapter. Sorry.
Sir, before going to the next question.
Yes.
Hello.
Yes, sir.
Sir, can you just briefly make me understand this concept of rotationality and irrotational flow? Because if you are taking a elementary element within the flow field, how can we define that it is means not mathematically? If I am considering it practically, then how can we visualize it as an irrotational or rotational flow?
Okay, I will tell you that. Suppose I will use the one more new slide. Okay. Let me use the same diagram. Are you able to see this diagram, right? So now see, if you are considering any fluid element in a flow field, consider in two-dimensional way for your simple understanding, and because of the flow velocity and the flow properties, the fluid element will definitely distort in the sense the edges. Now though you consider the fluid element is initially rectangular, and like this, if you consider any fluid element, always at every point there is velocity. This is x velocity u and this is y velocity v. This is also fluid element and this has some distance, that is say dx, this one is dy, this one. I just introduce few mathematical terms just for your understanding. Later you will see it physically. I will tell you complete in physical manner. So if you move along this element of dx length, your velocity v become v plus dv, a small increment in velocity. In the same way, if you move along this element in the this y direction, that u velocity will be u plus du. See, now you have difference in velocity at this point 1, and difference this point b, and sorry, this point a, b and c. The same notation I'm using here. This c, the same notation I'm using here. Point a, point b and point c. We have three different velocities. These velocities v plus dv may be compression, maybe high velocity or low velocity, or maybe same velocity, whatever it is. Let's assume that u plus dv is greater than u plus du is greater than u, and v plus dv is greater than v. If you assume like that, definitely u and v will convert your entire fluid element from point 1. This is your point 1. As is your fluid element will convert to point 2 in the time. I'm saying in the time. Will convert means it will move from this point to this point, but this additional velocity, that is dv and du, these additional velocities will deform your element, the edges what you have, these edges will deform like this, like the way you are seeing in the point 2. So it is clear that every element in the flow field will deform, but to understand whether it is rotational or irrotational, you need to see whether any significant amount of rotation. Now you can see in this edge from the y-axis, and this is x-axis. From the y-axis, I have say approximately 45 degrees of rotation of this edge, okay, but in the this axis, from x-axis to this edge, there is say only 10 degrees of rotation. If there is a large amount of difference in rotation, then what happens to this remaining 35 degrees of rotation? That means this particle have a tendency to rotate about its own center. You're getting? So if a particle is rotating about its own center of axis, this is the center of axis of a particle. If it is having tendency to rotate about its own center of axis, then we are saying it as a rotational flow. It is deforming, but it is having a net angular velocity that is rotating about its own center. This is your center of axis. But in rotational flow, your deformation, this axis and this axis, say it is 45 and this will, sorry, it won't be 45, this is 30 and this is 30. So your deformation will be always same from this side, from this side. So this kind of flow is called, sorry, yeah, this kind of flow is called irrotational flow, but it is highly deformation. You got it, Ahid?
Yes, sir. Just another question to add,
Yes,
since I
yes.
have a doubt regarding this. Sir, if we are taking any irrotational flows, there are relative velocities between these 2 points. Sir, should we assume that the flow is also viscous? The viscous forces are acting on these forces. It is a viscid flow or compressible flow before we are assuming that it is an irrotational flow.
No, no, there are no assumptions. If you have any velocity vector, first you need to check whether that velocity vector is possible or not by using your continuity. Suppose my velocity vector is v is equals to u I cap plus v j cap plus w k cap. This is my velocity vector. The initial thing I need to check is the real existence of this velocity field by using the del dot v bar or the continuity, actual continuity equation. If you have the density field del rho bar v bar, or you can use this compressibility equation also. This is kind of compressibility equation, or you can also call it as continuity equation. There are some conditions. So you need to check whether this velocity field really exists in nature or not. That can only be verified by these continuity equations. If it is compressible or incompressible, you need to verify that velocity field. If it is satisfying this equation, then you can directly apply whether it is rotational or irrotational. You can just directly use del cross V bar. There is no conditions that you need to verify inviscid or viscous, whatever it is. Let it be inviscid, viscous, or compressible or incompressible. That does not matter. You can find out where irrotationality or rotationality is a primary kind of parameter that you can find it in a flow field. It's not a dependent on any assumption.
Okay, sir.
So this is the question number 10. Shall we go for the next question? I think I forgot
Yes, sir.
to play. Yeah, I forgot to place 2 more questions, but let me pose those questions here. Yeah. Okay, this is going to be end of the slide. I will use the new slide. We have just 2 more questions here. Those are simple statements. The question is just like this. If you have a line integral and that is say v bar dot ds bar velocity or anything of line integral, what is the relation that converts this line integral to the area integral, or what is the theorem that is helping that is giving us to convert the line integral to the area integral? This is the question. And if you are you like, if you know the theory of it, it is easy to say that it is a Stokes theorem for that vectors. For the vectors, because you see it is a v bar and dot ts bar. I'm using these two are also two are vectors. Okay, for vectors it is called Stokes theorem. Okay, you are dotting the two, like this is a line integral. So this is a line and you have v bar and the ds bar is like this. You are dotting two products along this line integral. And now instead of line integral, I want to do area integral. So I will take this area, these two integrations are same, that given by the, proven by the Stokes theorem. one can convert the line integral to area integral or area integral to the line integral. That is called Stokes theorem. In the same way, surface integral, if you have this surface integral like this, I'm considering this is a 3D volume, say it is a 3D volume, and you have the surface like this, okay, or let me draw more clearly. This is your 3D surface, and you have a surface integral like this for shear stress. This is a small elemental area dA. For calculating the shear force, you are doing the surface integral of shear stress over entire surface. Instead of, you can also do a volume integral. This is a volume integral V bar. It's a V volume dot shear stress dV. The relation that converts the shear stress to, sorry, not shear stress, the volume integral to the area integral to the volume integral. This is called divergence theorem. You can convert the area integral to the volume integral by using the divergence theorem. Okay, this is the question. And the last one is mass conservation equation in integral form for a finite space. Let's write the mass conservation equation. Suppose d by dt integration over the control volume dv plus integration over the control surface rho u bar at dot n cap ds is equals to 0. This is mass conservation. The question is, what are the integrals that we are able to see in this mass conservation? We are able to see one volume integral and one surface integral. This is the question. So in mass conservation, we have only volume integrals and surface integrals. Okay. So this ends our discussion of this particular one. Let's see the continuation of it. We have some, now we will see some concepts of last week content taught by the professor, and we will go for solving some other problems. Let me open the another PPT. Okay, let's move to the directly to the content of this chapter. So from our last lectures, from the last week lectures of professor, we learned many important formulations regarding the fluid mechanics and aerodynamics. But most of these particles, most of the content always we can see in fluid mechanics, and some of the important contents are mostly in deep coming from the aerodynamics. So I will just give you the overview of those contents, but not in deep of every theory or the derivation of it. I'm just giving what are the equations that are necessary for today's problem. We can see the remaining part in next classes, but let's see the important few things. The first thing is substantial derivative. What is this substantial derivative? Suppose at point 1 to point 2, you have a fluid element like this and another fluid, same fluid element convected from point 1 to point 2 in that both time and space. It takes some time, right? So in from point 1 to point 2, it converted in both time and space. Now this point definitely, or this fluid element definitely have the properties like pressure, velocity, density, temperature, everything. So this is P1, V1, ρ1, T1. In the same way, P2, V2, ρ2, T2. Now, how do we identify, how we can find this rate of change of any particular parameter, any primary variable? These are all primary variables in the both space and time. That rate of change of these properties of primary variables or any variables in both space and time is we call the substantial derivative. So let me write in more mathematical way. Suppose you have density, I am taking as density as a reference. Density as a function of x, y, z and t. You have density rho equals to rho of x, comma, y, comma, z and t at point 1. This is your point 1. If I want the density at point 2, how I can write? And it is a, remember, this is a function of both x, y, z and t, all the three spatial parameters and time parameters. So at rho 2, we can write it is a rho 1 plus dou rho by dou x at point 1. This parameter, this variation should be at point 1 times x2 minus x1. We can also write it as a del x, that is distance between x1 minus x2 minus x1. And same way, dou rho by dou y, this partial derivative should be also at the point 1 and the change in the distance. Similarly, for other things, dou rho by dou z at point 1, z2 minus z1 plus dou rho by dou t at t2 minus t1. So there is no matter of using a point 1 here. It's a time parameter. Time does not have the point. So like now if you see rho 2, we wrote the equation for how to identify the value of rho 2 based upon our Taylor series kind of expansion using the chain rule like x, y, z and t as a function. These are all the primary variables that governs the density. And now we just wrote how to write the rho 2 if we know the information of at the P1, I mean at the point 1. So if you divide the entire parameters by T2 minus T1 is equals to del T. If you divide and further simplify, you will get dou rho by dou T. Here also you are dividing it T2 minus T1. That's why we call dou rho by dou T is equals to U dou rho by dou x plus V dou rho by dou y plus W dou rho by dou z plus dou rho by dou t. So this is what our substantial derivative is. It's not only valid for density, it is valid for any other parameter. So it can be generalized by this way. D by dt is a capital D that we call a substantial derivative, which includes, let me reorder it, that is dou by dou t, the time parameter first, and then the spatial variables, dou u dou by dou x plus v dou by dou y plus w dou by dou z. So now this first component we call as local derivative. Okay, and then this component we called as convective derivative. The change of any property because of changing its position. You see these parameters are x, y, z. If any properties is changing, when it is changing from position to position, that particular derivative or that rate of change we call as a convective derivative. If it is changing only because of the time, then we call it as a local derivative. Okay, so this is what the substantial derivative uses. For more detailed understanding, Professor had thought the examples of convergent divergent section or some important flow phenomena where this dou by dou t only convective derivative exists, only local derivative exists. There are some good examples are there. You can refer it the last lectures. So how this substantial derivative works. This substantial derivative further written or further classified as, for the simplification, one more step in from the vector calculus, del, sorry, this is not del. This is further written as v bar dot del of one more parameter will come here. The parameter in the brackets can be any parameter that we want to simplify or we want to understand its local and convective derivatives. Okay, so this is all about the substantial derivative. Let's go to the, just a minute. It's not allowing me to go for next slide. Okay, so now let's see about the x momentum equation. So in nature, every fluid flow shows some particular Reynolds number if it is flowing over a body. Suppose a flow is there and you have a cylinder here or any object flow over this cylinder. This is not the actual drawing, but let's assume this is a cylinder and the flow is passing over the cylinder. Then the Reynolds number is a key parameter based upon the characteristic length. Suppose if your diameter is d of the cylinder, then Reynolds number can be calculated by ratio of inertial forces to the viscous forces. The ratio of inertial forces to viscous forces. This is based upon further simplification by substituting the inertial forces and viscous forces, that is rho v d by mu. You can see the mu is the viscous coefficient and rho is the density, v is the velocity and d is the characteristic length. Characteristic length means if the flow is over cylinder, the characteristic length is diameter d. Okay. So this is your Reynolds number definition. If the Reynolds number is the key parameter that decides what is the condition or what will be your flow structure, it can be laminar, transition, turbulence. So those things we will see in the later sessions, but it should be a very important parameter. This will also, this has been saying that if Reynolds number tends to infinity, flow becomes inviscid. Flow become inviscid. Why? Because if you just now see Reynolds number, if you substitute tends to infinity, the mu value or this value is going to be, the viscosity should tends to 0, this mu value. That is why we are saying the Reynolds number tends to infinity, flow should be inviscid. This is also proven by the continuity or the momentum equation. This can also verified by the momentum equation. So let me write the x momentum equation. The x momentum equation one can write like dou by dou t of rho u plus del dot rho u v bar is equals to minus dou p by dou x plus dou by dou x of tau xx plus dou by dou y of tau yx plus dou by dou z of tau zx. This is all our shear or viscous terms. Okay, now for understanding how this Reynolds number is affecting the flow physics, one can write in a non-dimensional play. If you have gone through the past lectures, the standard notation was used is u prime equals to u by u infinity. For the sake of non-dimensionalizing the equation, v prime equals to v by u infinity, p prime equals to p by p infinity, x prime equals to x by c, any characteristic length, and y prime equals to y by c. So all the dimensional parameters like rho, u, p, everything can be non-dimensionalized by using this kind of, this is how we can write by the non-dimensional way of the equation. Once you substituted these non-dimensional kind of parameters in the above equation, and then if you simplify, you will get u prime dou u prime by dou x prime plus v prime dou u prime by dou y prime is equals to minus dou by dou x prime of p prime by p infinity by rho infinity u infinity square plus half rho infinity c u infinity by mu times dou by dou y prime of dou v prime by dou x prime plus dou u prime by dou y prime. So this is the equation you will get once you substitute all these non-dimensional parameters into the momentum equation. This is just x momentum equation. So now carefully try to see this denominator. This denominator is rho infinity c u infinity by mu. I will write in the denominator only. That is, one can write this denominator as Reynolds number. The symbol is Re for it. We standard notation for the Reynolds number symbol is Re. So I am writing it as 1 by Re. Now, if you see this entire equation, if this is the Reynolds number at this point, if you substitute that Reynolds number is tending to infinity, 1 by infinity, this part, this entire viscous part will tends to 0. So that is how we can see that the Reynolds number is very high, your shear stress or flow becomes invisible. That is how it is defined. Okay, so this is one of the important point that we need to understand how the Reynolds number is affecting the flow physics. So let's see the next concept. We learned some of the important concepts of Bernoulli equation, Euler equation, and the using of continuity in those lectures. I will just give you a brief of those things for solving the problems, for upcoming problems. So, in the momentum equation of 3D inviscid flow, consider any 3D inviscid flow where viscosity is 0, and your momentum equation will like u dou u over dou x dx plus v dou u over dou y dy plus w dou u over dou z dz is equals to minus 1 by rho dou p over dou x dx. This is not dy, sorry, let me erase it. Dx is already written here. So this is your momentum equation, and for the steady state case, this is your momentum equation because there is no time parameters and there is a pressure gradient at the right hand side. If you substitute that curl of velocity v bar, that is you can see dou w by, you will get a big expansion of the determinant, the curl of velocity. I'm not going to write again, but let me show you the details of it, how it is. Curl of velocity dou w by dou y minus dou v by dou z, this part I cap, and minus dou w by dou x minus dou u by dou z j cap plus dou v by dou x minus dou u by dou y k cap. This is the curl of velocity, and you substitute this is a 0, and you will see dou w by dou y minus dou v by dou z equals to 0, and you can simplify this format and you substitute these formats in this continuity equation. I'm not going to in detail of everything, but this is a step what you need to do, and if you substitute back into this equation one, and for the simplification one will end up with Euler's equation, that is dp equals to minus rho v dv. This is a very powerful equation that one need to understand, which is valid for both compressible and incompressible flow. For both compressible and incompressible flow. So this is not only the curl of velocity, you can also substitute the del dot v bar is also, I think there is an important step is also there. So I suggest you refer back the derivation steps if you want to if you're interested in how to get this Euler's equation dp equals to minus rho v dv. So you can see those lectures and get back to your own, you can derive it on your own. So once you get the Euler's equation, it is valid for compressible and incompressible irrotational rotational flow. It is not any, there is no limitation for it. So after getting the Euler's equation, using some assumptions, like there are three important assumptions, with those assumptions only we can get the Bernoulli's equation, which is quite famous in fluid mechanics or anywhere, any fluid or aerodynamics mostly uses this Bernoulli equation. Bernoulli's equation derived from that, P plus half rho V square equals to constant. But this is not applicable everywhere. There are certain conditions where you can use this Bernoulli equation, and those conditions are strictly very important to follow. Let me see whether I wrote those conditions. No. Okay. But these conditions are only, I mean, this equation can only be applied when your flow is inviscid or sorry, irrotational, I can say. Instead of directly saying inviscid, it is better to say the flow should be irrotational flow, but we already taken this flow as inviscid here, so I'm not going to mention it again. Note that the first statement itself is our 3D inviscid flow. So after that, we are stating here the Bernoulli, for the Bernoulli equation, to use this P plus half rho V square is equal to constant, the flow should be irrotational. Inviscid is a common, inviscid is a must condition. I'm not going to tell this, it's a must condition because from based upon that assumption we derived this. And the second condition, if you are not able to see it is a judge whether the flow is rotational or irrotational, these are either any one of the conditions should be satisfied. If first condition is not satisfying, if second condition is satisfying, you can use the Bernoulli's equation. What is the second condition? The second condition is you should apply the equation only along the streamline in a rotational flow. If you have a rotational flow and you still want to apply the Bernoulli equation, you must identify a streamline in the flow field, then only you can use this Bernoulli equation. For example, if your flow is rotational and you identified a streamline here, and I have two different streamlines, this is psi 1 and psi 2. This I'm just identifying the streamlines with psi 1 and psi 2. I can, if the flow is rotational, remember that flow is rotational, I can apply the Bernoulli equation only on point 1 and point 2, between point 1 and point 2, or either point A and point B, because those points are only on the streamline. I cannot apply between point 1 and point B, or same way the cross points. It is not valid between the cross points or any other two different streamlines. It is only valid along the streamline. So in this condition also you can apply the Bernoulli equation. The third condition, it is mathematically difficult to understand, but if you can find out a line, not if you find out a line that is perpendicular to the vector given by curl of velocity. So curl of velocity, if you are able to find out a line perpendicular to curl of velocity, will give you one vector, say vector a bar, and this is a dl bar. If a bar, this curl of velocity, you got some kind of vector a bar. If these two vectors a bar or dl bar, dl is a small elemental line, and if you are it is quite complex. I'm not going to introduce this statement because it is also not discussed, but this is one third condition is also there. If you are able to, this third condition is also, if you can apply, then even though flow is irrotational, you can use the Bernoulli equation when you are going through a line that is perpendicular to a bar dot dl bar. Then it is applicable. The Bernoulli equation, again here also it is applicable. You should go along the dl bar. Don't worry about the third condition. Mostly you will see in this basics level that you get the first condition and the second condition. You should remember the flow should be inviscid, irrotational, and along the streamline. And one more condition here is incompressible. After this one, in the Bernoulli equation, the flow should be incompressible. So all these conditions one should understand before applying the Bernoulli equation, whether all these conditions are satisfied or not. Then only you are able to apply the Bernoulli equation. Okay. Here, one more important, this is the pressure, and this half rho V infinity square, if you see, half rho V square, this I can write half mass by volume V, I will say volume by V square. This half mv square is the kinetic energy from our basic physics. So half rho V square is nothing but a kinetic energy per unit volume. You should keep in mind this is just a kinetic energy of the flow field, local kinetic energy of the flow field per unit volume of the flow field. Okay, fine. So let's go to the next concept, that is compressibility. Compressibility is very essential to understand when your flow is going to certain conditions. When you have the high velocity fields and your density change up is very significant, then you need to, it is very essential to understand the compressibility features of a flow. Suppose you have a very high speed of velocity, say V infinity is equals to 200 or 240, whatever the meters per second. At this velocity, or even that differs with, we can change the very high velocities, low velocities, but at a certain, after certain velocity, your density in the flow field, like d rho by rho. So suppose my velocity at this point is 10 meters per second. If suddenly it is accelerated, or even though slowly it is accelerated, suppose it's achieved up to 250 meters per second, because of this high acceleration of the flow, my density at rho 1 and rho 2 is changed from rho 2 minus rho 1 equals to d rho, I can say, and say rho 1 by rho 1, what is the initial density. If this change in density between point 1 and point 2, initial velocity, remember that again I'm telling your initial velocity is very low, 10 meters per second, and you are accelerated to up to 250 meters per second. Because of this, you got a change in density, that is rho 2 at this point, and this is rho 1 at this point. So change in density is rho 2 minus rho 1, that is d rho, by the initial density, that is change in density by initial density. If it is greater than 5%, this change is 5, which is greater than of your initial density, then we consider that the flow field, whatever the flow field velocity parameter that is going on, or under compressibility effects, or the flow field is compressible. This is the key definition that one should keep in mind all the time. What is the condition or requirement to say the flow field is a compressible? The flow field is compressible means the change in density by initial density at that starting position should be, the change in density should be greater than 5%. Okay, this is the pure basic definition that mentioned for understanding what is compressibility and what is the limit that's set for this. This is set based upon the engineering levels of requirement, and this density compressibility is defined. So you have compressibility can be written as the definition. What is the a good definition for the compressibility? Say compressibility is, you can write tau or k. Compressibility sometimes people define it with the k or tau, whatever it is. So let me use tau or k, anything, and that is equals to 1 by v. This small v is a volume, or you can say it is a specific volume, and this is dp. So if you segregate this, I just wrote some equation, but what it actually means is you just need to segregate and see. If I segregate and see, the top parameter is change in volume, the fractional change in volume per unit volume, change in volume per unit volume, per change in pressure or change in that, because of any, because of flow field or because of external force, whatever it is, there is a unit change in pressure, the corresponding change in volume per unit volume is defined as the compressibility tau or k. It just needs some understanding like how this compressibility is defined. So with that, we got compressibility k equals to minus 1 by specific volume v dv by dp. Okay, so it is better to write in some other formulation, like instead of dv by dp, it is more convenient if you see density times specific volume is 1. It's just both the same definition, and v dou rho plus v dou v is equals to 0. That is obtained by using just applying the differentiation of d of rho v. If you apply the differentiation of d of rho v using the chain rule, you can get this product rule. So you can use these two relations for simplifying this compressibility and writing in another way, like compressibility equals to 1 by rho d rho by dp. You see, this is d rho by rho, and this is dp. This suits well for our compressibility condition stated here. So this is how you can write, but for further details of this compressibility and these relations, how it is simplified, you please refer to the lectures notes and get good understanding of the derivation. These are all the outcomes of, final outcomes of those derivations. I'm not going in details of this. So next concept is, this is up to the compressibility. So let's not go in deep of compressibility now. I will show you few things that only in incompressible flow, and regarding the Bernoulli equation. I will go to the next slide. So this is a question slide. I will add one more slide. Okay. So now let's see how we can use the continuity equation and how we can couple the continuity equation with the Bernoulli equation in this slide. The continuity equation in integration format is like this, that is dou by dou t of This is a volume integral rho dV. We already seen in the previous problem, one of the previous problem, and this is a surface integral v bar dot ds bar equals to 0. This is your integral form of the continuity equation. And then if you apply this continuity equation for a one-dimensional flow, and further simplify this with a good sign convention, apply the sign convention also. And constant density is constant, incompressible. Okay, you should clearly see why I wrote constant density as a different and incompressible as a different. Like before coupling this, I will give you the clarity of what is this constant density and incompressible flow. We just seen the incompressible definition is dou rho by rho should be greater than 5%. Dou rho by rho should be greater than 5%. That means will our density won't change below 5%? If the density change in 5% is not considered as compressible, yes. If the density change is below 5%, that is not considered as a compressible, compressible flow. That is considered as a incompressible flow. So this is what incompressible flow. Also, one more condition for incompressible flow is your del dot V bar should be equals to 0. This is a condition obtained from using by taking the elemental volume. This is looking like a continuity equation only, but this is the basic definition for the incompressible or to compressibility relation. If it is del dot V bar equals to 0, then your flow field is incompressible. But constant density means the substantial derivative of density should be equals to 0. These two are different. So that's why incompressibility and constant density are both different. One can understand there are some cases where flow is incompressible but density is constant. That is, there are some cases that I'm not going to do in details of that, but you should realize that dou rho by dou t equals to 0, that gives you the constant density flow field. If del dot V bar equals to 0 and dou rho by rho, I mean change in density by unit density is less than 5%, that will give you the incompressible flow field. With all these conditions, if you apply in the continuity equation, and yes, sir.
In the concept of this constant density, are you taking substantial derivative of rho is equal to
Density,
0? Or
yes, the substantial derivative of
okay,
density should be equals to 0.
okay, sir.
Okay. So now if you apply all these conditions to the continuity equation and one-dimensional flow, remember that you have only one-dimensional flow, that is u only x varies only in the x, where x and u are the only parameters that you play, and then you will get the very famous relation from our basic physics is a1 v1 equals to a2 v2. This is what we call as generally a continuity equation in algebra form, and since density is constant, you can cancel out on the both sides. Okay, this is one of the key important equation that you need to remember for all the time in the flow fields. But applications and its conditions also you should keep in mind. It is not valid for all the cases. Density should be constant and all these things should be satisfied. Now let's couple this continuity equation with the Bernoulli's equation. We have Bernoulli's equation is P1 plus half rho V1 square equals to P2 plus half rho V2 square. How we can couple means, here is we have velocity V1, here is the velocity V2, V1 and V2 we have. So just substitute this in the Bernoulli equation. If you substitute like that, then you will get P2 equals to P1 plus half rho V1 square minus half rho A1 V1 by A2 square. So now we just substituted it, and this is a coupled form of Bernoulli and continuity equation, which will be useful so many times in calculation the flow that where aerodynamics or aerodynamic usually encounter in real life or for its experimental purpose. This is a very common kind of equation, valid only for the subsonic cases, sorry, incompressible also, and all these conditions also must be applied. Whatever we seen, all these conditions must also be applied for that. Okay, few more things that I need to discuss now. This is Bernoulli equation, but we already know the Bernoulli equation in this format, like P plus half rho V square is equals to constant. And I should also tell the concept of stagnation pressure. The stagnation pressure means, suppose you have a flow field here, or say you have a big drum here, or a big cylinder, spherical vessel. This is a spherical vessel, and in this spherical vessel you just opened the throttle here. This is your throttle valve. You just open this throttle valve and the flow will come at certain velocity v, and it is having at this exit, suppose velocity and pressure is p, but this is at the pressure p naught. Say this entire pressure in the spherical vessel is at pressure of p naught, like high pressure. Best example is when we go to any cycle shop or any boilers, or you can see the boilers are very big relative to the, not only boilers or the cycle, like the cycle shop, or the air vessel is there. In that vessel, that exit, that where how you fill the air to your cycle tire, that exit is very small compared to the pressure vessel of that air vessel. So the pressure inside that almost stays constant. It decreases very slowly like a quasi-steady process, but here the velocity and pressure are variables at the exit. So inside the velocity is almost constant. V inside, that is V naught, is almost approximately equals to 0. So this is an important concept that you need to understand. If you apply the Bernoulli equation, say assume that all the Bernoulli conditions are satisfying and flow velocity is also within the limits of incompressible. If you assume and apply the Bernoulli equation, P naught plus half rho V naught square, I will substitute the values later on, plus P1, or this is a P1 at the exit and V1 at the exit, P1 plus half rho V1 square. The density is not variable, please keep in mind that. Now just substitute that V naught equals to 0. If you substitute V naught equals to 0, P naught equals to P plus half rho V1 square. This is P1. So this kind of pressure where the velocity is 0, we called as stagnation pressure or the total pressure. The both are same. So we call this kind of pressure is called stagnation pressure, where the velocity is 0, but there is a significant velocity at the exit of the throttle or the exit of the opening. There we have the pressure P1, different static pressure and a different kinetic energy. This total pressure is converting, or the stagnation pressure is converting into static pressure and the kinetic energy. This relation is only valid for the incompressible kind of, or the Bernoulli equation also, what are the conditions that you're following, only for those conditions it is valid. But if you go for the compressibility, you need to come up with the Euler's equation, that is dP is equals to, let me write it, yeah, dP is equals to minus rho V dV. For deriving this kind of relation between static pressure and stagnation pressure, this is static and this is stagnation, you know, this is stagnation, and this is the kinetic energy. So deriving P naught equals to P1 plus half rho V1 square, this is valid for only for incompressible flow. For compressible flow, if you want to make a relation between stagnation pressure and static pressure and kinetic energy, you have to definitely take from the compressible relation, sorry, that Euler's equation. You should not come from the Bernoulli's equation, because there the density we already stated should be as a constant. So in a compressible flow, P naught is not equals to static pressure plus kinetic energy. Is the kinetic energy per unit volume. The stagnation pressure, static pressure, and kinetic energy does not equals in compressible flow. Very essential thing that one should keep in mind before applying this for the compressible and incompressible flow. Okay, and that's those are the key things about application of Bernoulli and its compressible and incompressible. Let's go to the next concept. There are so many important concepts in this chapter, so it takes some time for me to give you the importance of the equation of every parameter or every variable. Let's go for one more thing, that is pressure coefficient. The pressure coefficient is defined as Cp is equals to P minus P infinity, is defined as P minus P infinity by half rho infinity B infinity square. What is this P minus P infinity? How you can understand this? Suppose you have a point B here and I have a point A here, and my flow is coming on to the airfoil. My airfoil is steady. I'm testing my airfoil in the wind tunnel or some kind of equipment I'm using to test this airfoil scientifically. Now at this point A, you know the velocity, pressure, everything are all free stream. Those free stream means whatever the incoming velocity parameters or pressure parameters, everything we call as a free stream parameters, that we subscript, that we indicate with the subscript infinite, like this, V infinite, P infinite, rho infinite. Okay, so these are all important conditions that you should know before testing any of the objects. So these are all my pressure P infinity, rho infinity, V infinity, and after going this flow on top of the airfoil surface, my pressure becomes, suppose at this point P, my pressure becomes PB. My pressure becomes a point PB. Now if I want to say, instead of a non-dimensional form, I want to say like someone, someone person, that I should say that a pressure at point B in a non-dimensional form. How I can say is, I will just calculate that pressure at point B is PB by, this is the coefficient of pressure at point B, by of rho infinity V infinity square. Like that I will calculate the non-dimensional pressure coefficient on that point. This is very useful while understanding or an aerodynamist to study the aerofoils and pressure distribution over it. Once you understand the pressure distribution flow physics on it, you will you can judge many parameters. So this coefficient of pressure is very critical to learn or to dig more of this concept. So if you can use the Bernoulli one again, once again let's call the Bernoulli, that is, we just seen that like this, but P plus half rho U infinity square equals to P1 rho U P infinity, and this is P plus half rho U square. Okay, so just substitute instead of these things, like if you just write like this, like writing is between 2 points, you can also write it as a constant, right? So use this constant at the right side and you substitute this half rho V infinity square in this, and because of this minus, this constant will go away, and one can write this Cp is equals to half rho rho U square minus half rho infinity U infinity square. This is not also, this is also rho infinity, okay, because density is not our variable. This is also rho infinity by half rho infinity U infinity square. If you simplify, if you cancel out the density, you will get 1 minus u by u infinity square. So this is the simplest form of a pressure coefficient for the incompressible flow. If you can use either, if you know the pressure field on the aerofoil or pressure field of the free stream, you can use this relation. This is the basic relation. Or if you are in incompressible flow and satisfying the Bernoulli's condition, you can also use 1 minus this condition. Also you can use 1 minus u by u infinity square. Let me have some water. Okay. Yeah. So this is also useful relation for our problem solving things. So please keep in mind that how to use this pressure coefficient based upon static pressures and based upon the velocity. You can play with these two things. Okay. Yeah. Just a minute. Okay. Let's go to the next one. That is, yeah, one more point is static pressure is equals to, that pressure coefficient is equals to 1 for, if you are measuring the pressure coefficient at a stagnation point, for a stagnation chamber or stagnation point, then the Cp equals to 1 for stagnation point in, again the condition is incompressible flow. Okay, good. Now one more important thing is Cp does not equals to 1 for stagnation point in compressible flow. Don't confuse here, this is incompressible and this is compressible. Okay. Now few more interesting concepts are I will tell you few things that is related to the present thing. Suppose we already seen that del dot v bar equals to 0. This is the continuity, you can say it's a continuity equation or also standard compressible equation, and this is, one can write that v bar equals to del pi only for irrotational flow, that is del cross v bar equals to 0. If you del cross v bar equals to 0, then one can write v bar equals to del pi, where pi is equals to potential velocity or velocity potential. We call generally as a velocity potential. So just substitute that del pi in continuity equation, that is del dot del pi equals to del square pi. We call this kind of format in calculus as a Laplacian equation. You can see it by expansion of it, that is del square pi is dou square pi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square. This is called a Laplacian equation in the calculus, and very useful thing, very important one to find out the solution in terms of the velocity potential, like to solve the Navier-Stokes equation in inviscid flow. This potential function is highly useful and highly utilizing. Like for some, what a good example is, if you have a uniform flow, let's see how we can write the pi in for this uniform flow. Uniform flow means you should have velocity vectors parallel to each other. It can be any domain, not only xy, it can be any domain. The velocity vectors should be parallel to each other, and the velocity should not vary with any x and y coordinates. U should be equals to u infinity. U should be equals to u infinity means constant. It should not be a function of x comma y comma z should not be function of it. U should be constant and v should be 0, any y velocity. If u equals to infinity and v equals to 0 and there is no z component, this is what we call as, these conditions are called uniform flow conditions. Okay, now with these conditions I want to write the potential function for this. We already know if v bar equals to del pi, I can write that u I cap plus v j cap plus w k cap is equals to dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. This is the important relation. From this, u equals to dou phi by dou x, v equals to dou phi by dou y, and w equals to dou phi by dou z, right? Use the same relations here to find out the potential equation pi for a uniform flow. So u equals to, u infinity equals to dou phi over dou x, and v equals to 0 equals to dou phi over dou y. I already discussed this, how to find out the pi in the last lecture, in the last week lecture. So we can simplify. I will just show you how to simplify this again. You just need to integrate, like dou phi, separate the variables. Dou phi is equals to u infinity dou x, and you just integrate it. You will get pi equals to u infinity times x plus function of y. Why you will get function of y? You are integrating with partially x. There is no discussion of y, so there should be some function of x which was gone by due to the partial differentiation of the pi function with x. Okay, in the same way, if you do for integral pi 0 dou y, you will get pi equals to 0 plus z of x. Because why, same way, the logic is same. Again, you are doing the partial integration with y. That means there should be some function of x, that is g of x. Compare now first function and second function. In the first function and second function, there is some value or some parameters, that is function of x, that is g of x, and this is called u of x. And in the second term, there is some function of y should be there, but here there is a constant. That means function of y is a constant which is equals to 0. So phi equals to u infinity x is your flow field. Why we need this pi equals to u infinity x? What is the need of writing the velocity field in this format? You are not going to use velocity field u equals to infinity x or u equal to something. We are not going to deliver all these requirements of velocity field u, v or w. We just say the phi equals to this much means we get lot many information, means that is the moment the pi you are giving of some velocity field is, that means the velocity field is irrotational. Okay, and it also satisfies the continuity equation, and it also able to give so the u velocity, v velocity. So only one single variable, that is pi, giving us this much of information of the flow field. So that is why we are interested on writing the flow field in terms of pi or in terms of size. Size is the stream function. Okay, instead of directly writing the things in u and v velocity, we are very much interested, aerodynamics are very much interested in writing the pi and stream functions. If you write substitute in stream function, then it will definitely valid for continuity equation, that is del dot v bar. Okay, del dot v bar also it satisfies. So this much, if you are giving some psi function of any flow field, that means it obviously satisfies that the continuity equation. So you don't need to worry about, or you don't need to solve it again. So that is the use of writing the flow field in other parameters like this potential function or this stream function or some other parameters. So these are the key concepts that we still have some important key concepts, but I would like to take some questions if you have for 10 minutes, or any discussion that would you like to do, or else if no questions or something, I will proceed for the one or two simple question solving.
Sir, I have few doubt.
Yes,
Means
sir. Yes.
yes, sir. Actually, I have seen the lectures from week 4,
Okay.
and I found some few doubts regarding that. Sir,
Okay.
this Kutta condition means, can you just explain this Kutta condition? Is the concept of Kutta condition?
Kutta condition. I just need to refer the notes what actually professor, because I don't want to derail your concept how professor taught you. But my
Okay, sir.
way, because I already seen the lectures, but I it's a very long back I seen, and I'm covering the
Okay,
past
sir.
lectures now. So anything that you want to see up to this particular concepts, I can give you the correct way. But let me try to explain you. It is almost every time the same. It is not a different thing.
Okay, sir.
So where is the question that you are um facing the problem, that Kutta condition saying that the flow should leave the trailing edge smoothly, or
Yes, sir.
velocity at the trailing edge should be zero.
Yes, sir. The velocity at the trailing edge will be zero, but there is a condition where the velocity flow field intersect each other. Means I cannot grasp that concept.
Velocity flow field intercept each other.
Means yes, sir.
And there is a slip
Means
that you
it,
understood,
it
that there is a slip of velocity because of this vertex sheet. Anything that you discussed like this, I mean that he discussed
yes,
like
yes,
this
sir. Yes,
vertex
sir.
sheet. And did you
Yes, sir.
find there is a slip in velocity between across this sheet?
Yes, sir.
There is a slip in velocity, that is this, suppose if it is u1 and this should be u2. I'm not going to give the direction specifically, but there slip in velocity occurs if you see the derivation of it. And at the trailing edge, the Kutta condition is mentioning us that um, to satisfy this slip and to satisfy uh, the integration, the conditions of circulation kind of thing. I will give you the mathematical aspects of it by referring to it. As of now, I can clearly tell you that because of to maintain the flow at the end. Otherwise, what will happen is, because there is a presence of slip on bottom and top surface, and at the trailing edge, you should also have the flow field that is downstream. There is no more solid surface here, right? So there is no more the point of vertex sheet presence here.
Yes, sir.
So your flow should be at the trailing edge is not constrained to the presence of slip because of this vertex sheet. Okay, and there are few concept of the stagnation point appearance at the trailing edge. There are stagnation point appear here, and stagnation point appears at the trailing edge also, sorry, leading edge also. At the leading
Sir,
edge also at
actually,
one.
in
Yes.
Sir, actually, I think in Kutta condition they are taking incompressible inviscid flow. That's why at leading edge there is a stagnation point. Means they are also analyzing during the in professor's lecture. I saw that in a cylinder, the
Mm.
flow field in a cylinder, and from
Mm.
that means that doublet, the concepts of doublet and combined flow of doublet, vortex point, and uniform flow. In that, they have
Okay.
the flow separation does not occur in that case if incompressible flow. I was confused in that means concept actually, sir, in
Flow
Kutta
separation
condition.
definitely, yeah, flow separation definitely occurs. Um, just to see, flow separation does not occur because we are considering uh, what is this one? Flow is inviscid and it is a potential flow. Potential flow he defined already. What is a potential flow? Arhit?
Hello, sir. Actually, your voice is
Okay. Do you, Professor, define what is the potential flow already in that? I think
no,
he
sir.
might
I
have
can't recall. I can't. Yes, sir. He might
potential.
have,
Yeah, yeah. It should be. It should be.
but I
But
can't
try to.
recall, sir.
Okay, just try to see what is potential flow. But I will give you the physical
Okay, sir.
insight of what is Kutta condition. Suppose,
Yes, sir.
let me see you. But from the very first beginning, Professor told you that if the flow is in front of an airfoil like this, it will give you the momentum to the flow, right? Sorry, it will give you the pressure distribution on the airfoil, and it will turns the flow because of this shape. It will turn the flow to this direction, right? Downward or upward because of the
Yes,
solid
sir.
surface,
Yes,
it
sir.
will turn the flow. Because of this turning,
Yes, sir.
the momentum, just if there is a change in direction or change in force, definitely there is an exchange of momentum. So momentum exchanges with the airfoil, so there is a net lift force or drag force. I'm not going to tell about the drag force as we are talking in inviscid flow. So there is a net lift force. Okay, so if you are telling like that because of this turning there is a presence of lift force, and in the condition of Kutta, if you are not applying that any two conditions like velocity at the trailing edge from the top surface or bottom surface should be equal, V1 should be equals to V2, or both should be equals to 0. Either velocity here at the 0 or velocity should be even and equals to 2. If nothing is applying, there should be a presence of stagnation point. If both are not true, they will cancel each other. First, if it is V1 equals to V2, first relation, that is V1 equals to V2, from the velocity from both top and bottom surface, then they will cancel each other, and there is a flow field exist here. If it is not V1 equals to, I'm telling in physical sense, if it is not V1 equals to V2, there should be an existence of one more stagnation point from your understanding of flow over cylinder. Suppose here it is a flow field you are existing. Suppose the stagnation point is existing here. Are you able to understand?
Yes. Yes, sir.
Yeah. See, from your understanding that did you find the two stagnation points on the flow over a cylinder?
Yes, sir.
Yeah, so in the same way, you should able to see one more stagnation point on the airfoil also. If that stagnation point at the not at the trailing edge or somewhere here on the top surface or bottom surface, so definitely the flow should come take a turn completely on the trailing edge and take back comes to the stagnation point. You see, it is completely turning 180 degrees. That means the velocity should be here, or what is the source that it has to turn completely 180 degrees to reach the stagnation point. So this position of the stagnation point is physically not acceptable because this flow cannot take the complete 180 degrees turn and reach the stagnation point, right?
Yes, sir.
Means that velocity should go reasonably here more than infinite. Like it should accelerate high, very amount of high acceleration should be there here. That is not physically possible. In the same way, if you point the stagnation point here, this upper surface fluid should also come to downwards like this and it will move from here. This is also not possible. So
No,
what
sir.
is physically possible? Presence of stagnation point at the trailing edge, right? If the
Yes, sir.
stagnation point is present at the trailing edge, either top surface and bottom surface should have same velocity. They should leave the trailing edge smoothly. Then only the flow field is physically possible. That is V1 equals to V2. Or else the both velocity at this point should be equals to 0. Then only the flow field should be exist. Right? This is a
Yes,
physical
sir.
condition that Kutta adopted to model the flow field on the airfoil. Got it?
Got it, sir.
So you keep in mind how the flow field is responsible with respect to the stagnation points. It is completely your way, like whether you're placing the stagnation points on top of this and bottom of this. If you're placing like this, how flow field is reacting to that, how flow field response will be that. Is it physically possible or not? Just because it is not physically acceptable or not possible, the Kutta condition stated like that. Okay.
Okay, sir.
Okay. Any more questions?
Yes, sir. I have another question
Yes.
regarding the force distribution and momentum generated in an airfoil. Sir, actually, I am finding it difficult to visualize this concept of moment at the leading edge. Sir, can you just explain it? Means
Moment at the
uh,
leading edge, that the resolution of
moment.
forces.
Yes, sir. Moment at leading edge, moment at quarter chord, and moment at XCP. That the force in that video, I have seen that video. Sir is taking three conditions and
Okay,
equating it.
okay. Let me tell you in my way what sir has taught you. I am not able to recall it now, but I will tell you in my way. I will take one more new slide. So let's consider a flat plate or the chord line. Instead of taking an airfoil, for your ease of understanding, I'm taking only the chord line. Okay.
Okay, sir.
And
Okay.
now this is the chord length C, and it is always a usual practice. Think in a practical way so that it will be very useful for you to understand. It is always a common practice that fixing up the point. Suppose if you are measuring the forces on aerofoil or a wing, you should fix that wing with some point or the entire surface. You should fix the entire surface or the point you should fix. So it is a thing like that we are fixing this point at like where we are measuring the forces and moments, means that is C by 4 from the leading edge. This is your leading edge point and this is your trailing edge point. Up to this, is this clear?
Yes, sir.
Now suppose because of the incoming flow you are facing this kind of counterclockwise movement. It is easy to understand because the flow is coming like this and it will tilt the plate in the counterclockwise, sorry, yeah, clockwise, right?
Yes, sir.
Think in a physics, it will always tilt. The flow is coming like this and it is always tilt like this. Whether it will tilt clockwise or counterclockwise, it depends on the airfoil shape. But the flat plate, I'm telling like this for your understanding. And there will be a force that is normal to this plate, that is normal force. And for the time sake, the drag force is not our concern as we are taking inviscid flow, or drag can also be considered, but it's not required now. Okay, so let's see, this is movement at C by 4 quarter chord point. This is movement at quarter chord point. Okay, and this is the force at quarter chord point. Force distribution on the entire surface won't vary if you take the point here or here, anywhere on the surface, because this is a resultant force. Already we took the average of forces by integrating the pressure and surface on the shear stress, everything we integrated and we took the average of everything, and the resultant force is the normal force. Okay, and the moment is also a resultant moment. Now if I want to find what is the moment at the leading edge, sorry, if I want to find what is the moment at the leading edge, there are no external forces, no other forces, but I want to find how much of moment is acting at the leading with respect to the leading edge. Moment at the leading edge is just equals to moments at the quarter chord point. What is the moment at the quarter chord point? The same moment will act there, plus you see this is creating a one more clockwise movement. What is creating the force? Normal force is creating. Normal force times moment is nothing but force times distance. What is the distance between this normal force and the leading edge? This is the normal
C
force
by 4.
and C by 4. That's it. It is the most common
But
practice. Hmm.
sir, actually, I think it will be negative before this in C by 4.
Yeah, sorry, because it is distance is in the left side, right? If it is
Yes,
on the
sir.
right side, the distance, if it is the left side, you will get a counterclockwise movement because of this n. This is negative, right? You're right.
Sir, now actually my confusion is this, that
Mm.
this MLE moment at the leading edge
Mm.
means how we will understand this moment, because we know that moment is normal force into the distance between that point and the action line of action of that force.
Yeah.
So, sir, how can we visualize this moment at the leading edge? Because
You are not. Yep. There is no.
distance means acting before this moment means I'm not getting it. This
No.
moment at that leading edge.
Okay. Don't take in distance presence or not, or anything is present, or don't take in like that way. Suppose you are an
Okay, sir.
experimentalist and you are doing the experiments. Okay.
Okay, sir.
And you have an airfoil like this. You have an airfoil like this, and you are doing the experiment, and you are want to understand the moment and lift distribution on this airfoil. Then how will you do? The common practice, as I told, first you will always take you will always fix the location at a point that is quarter chord point, that is from the leading edge it should be C by 4. If you are having a force sensor that is able to measure the movements, lift and everything, will you get the moment, force and drag everything at this point with that force sensor?
Sir, about this point,
About this point,
I think so, sir. We can get.
yeah, we can get. At the same time, if you are fixing about this point, will you get
Yes, sir.
this point also? It will show because it has a distance this side and there is a resultant force here. If you place your force sensor here, or if you place your force sensor anywhere, this will show the movement acting at that position. Force sensor does not know whether it is leading edge or trailing edge. It will show you the absolute amount of force acting at that point, right?
Yes, sir.
It is like you hinge a hinge here and the force is acting here, so the moment at this point means this force into this perpendicular. Are you able to see my cursor? I don't know. Let me
Yes, sir.
just.
Yes.
So it will take this force n into this distance to measure the moment here. Got it?
Yes, sir.
Yeah. Any
Sir,
confusion still? Hmm?
actually, I was visualizing this moment at that leading edge for cambered airfoil.
Okay.
Uh, so there is at certain angle of attack in
Hmm.
case of sorry in 0 degree angle of attack there will be lift generated for cambered airfoil. Since
Yes.
the stagnation point is shifting below the means mm, shifting somewhat
Upper
below the
surface.
chord point, and
Yeah. Hmm.
so actually I was thinking about that moment about the leading point, leading edge will be due to that shifting of that point, stagnation point.
Shifting of stagnation point. Who taught you that? This is already taught by professor that shifting of stagnation point is there
No,
in the camber.
yes, sir. Shifting of stagnation point concept was professor told us, but
Yes, it's
there
there.
was no
Shifting of stagnation.
concept like this because I was visualizing it.
Okay, you visualize in experimentalist way, like this is how you are
Yes.
going to measure the force movement, then it will be very clear. If you, it's
Okay, sir.
moment, force, resolution or everything is only because of your pressure and shear stress integration on the entire surface.
Okay, sir.
You just integrate what is the pressure distribution, what is the shear stress distribution, and then see the net resultant forces. That will give you the clear idea. If you are directly want to visualize from the pressure to movement, it is a wrong assumption. It will give you a wrong assumption
Okay,
because
sir.
it is the net effect of distribution over entire surface, right?
Yes, sir.
Yeah. But today it's a nice interaction with you, Arhit. Thank you for joining. I hope I can get few more questions. If not, we can end this session because we are already running out of time. So thank you everyone for joining this session. Let's meet in the next session next Friday. Okay. Thank you
Sir,
all. Yes, Arhit.
sir, can we get this lecture video of yours this doubt session by any means? Because
Yes, you can. I'm already sharing it. That NPTEL team is already sharing with you, right? Through problem solving session in the way you are watching the lectures. There is a problem solving session at the bottom.
Okay, sir. Sir, actually, in that section, only professor's video is only Professor Arnab Roy's video is only coming in problem solving.
Problem solving section, you will find a spreadsheet. You just drop a discussion in the Google form. I will send you the link to that Google form. I mean, Google form is there, right?
Okay,
You just raise this question. I will
okay, sir.
send forward the copy the link to that.
Okay, sir. And sir, another thing, since I am from mechanical background, and there is no faculty here who would help me regarding this aerodynamics, sir, I am finding many doubts while watching the video and solving the assignment questions, sir. For that, is there any means that I can contact with you or by anyhow, sir? For
For solving the assignment questions, to be
sir, not
strict,
for solving that assignment questions, just for
okay.
means that if I find any doubt regarding that video, like there are concepts of doublets and vortex sheet, vortex singularity. So that in that case also, sir, I found many times a doubt. So
Just directly drop the question in the Google form. If it is simpler one to explain you, I will respond or any other TA will respond directly to that. If it is a complex
okay, sir.
problem, I will take it to the lecture, or you just raise the same question in the every time in the Friday. If
Okay,
the
sir.
simple one to explain there, I will explain there, or else I will take it to the next
Okay,
session.
okay, sir.
Okay, thank you so much.
Thank you, sir.
Have a nice day. See you all. Have a nice weekend.